Welcome back to my channel and to this lecture series on the course of modular forms. And today we are going to start a new chapter. So whatever was in the lecture 0, we will say that it was chapter 1, and today we are starting with chapter 2, the modular group. So it just I'm the way I'm making these internship notes, I consider chapter 1 as introduction and motivation, and chapter 2 with the actual math. So in this chapter we are going to, and before that we are going to follow this book as I said earlier. And because the title is clear, the problems in the theory of modular forms, they will provide the theory, introductory theory of the modular forms in the way they prefer to explain theory in set of exercises. So most of the results are given in the follow of exercises, and which is good in a way that it is even easy to read. And I will strongly suggest this book if someone is preferring to take an course on modular forms for the first time, because when you try to solve the questions you will understand much more things, just what the question is asking. And without wasting any time, I will tell what we are going to cover in the chapter 2. The chapter 2 will have the full modular group, subgroups of the modular group, and Hecke operator and group acting on topological space. Now the funny part is, just like when if you ever had a course on elliptic functions, for the first few lectures you just read the theory and without no single example. I guess the similar thing is going to happen over here. In the chapter 2 and chapter 3 we are just going to develop the theory, and in chapter 4 we are going to see an actual example of a modular form of level 1. So there is so much to actually build up to actually read a stage where we read about this topic. So without again without wasting any time, let's start it. So I will just add the screenshot on the screen, I mean in the video, from my notes. So the definition of the full modular group is, it's a group, we will later see that it's a group. So the modular group is defined to be, the full modular group is a set consisting of all the matrices whose entries are integers and determinant is 1. So, and we say that it's actually SL to Z, if you know. Remember here the determinant is 1, not plus minus 1. And yeah, so some authors and some another way of seeing the modular group is from projective linear group, and here we take PSL, projective special linear group, over Z, and we define it to be, and it is actually defined to be as SL to Z modulo plus minus, mod plus minus identity. The way it's actually defined is, they are saying by this construction the quotient is plus minus identity, is that you will later see in the upcoming chapter, we say this modular group SL to Z actually acts on upper half complex plane H, and the way it acts, it's actually preserve the orientation. What I mean by preserve the orientation is, take an element, a matrix, say we are taking as identity and another as minus identity. Take an element from the upper half complex plane, say Z0, and I acts on Z0. I know where it will land, but for not just make it mess up, say it lands at Z1. then the matrix minus I acts on Z naught will also lands on Z1. So the orientation, the negative sign, it's not affecting here on the action we are going to discuss in the further theory. So that's why they actually define this in a way that as a modular group is a kind of projective special linear group over Z. So that's the role of why we have this construction. The orientation is preserved, and as we see, we define SL to Z as a modular group, the full modular group, or to be very precise. We take two matrices from this SL to Z and name to be S 0 minus 1 1 0, and another to be as T is equal to 1 1 0 1. I won't discuss too much right now, but don't take these two matrices too lightly. They will again come in the theory. I mean, they will appear occasionally, not occasionally, but yeah, again and again. And we are next going to prove that our modular group SL to Z is actually generated by two elements, S and T. Now, if you see uh, the order of this element, actually we haven't defined the group that SL to Z is actually a group. Under matrix multiplication, we are just going to show it later. It's actually trivial. So the next statement is over here. It's so easy, but when R is a commutative ring with identity, then SL to R is a group. So here R is Z, which is a commutative ring, and so SL to R, SL to Z, is a group under matrix multiplication, and this group is generated by S and T, where S and T are I just defined to be here, and with some calculation you should do it that the order of S is actually 4, and find out the order of T. It's so easy if you already have, if you are already familiar with the matrix. The order is infinite. So SL to Z is generated by two elements, one of whose order is 4 and another whose order is infinite. So the next theorem is, the very first theorem of this book. Not this book, but for this lecture series, is these two matrices generates the modular group. So SL to Z, our modular group is generated by, it's written over here only, so let's just skip it. So the proof is given in the book. It's so easy. Don't just think that you should read it. And the technique they are using will again be used in further theorems. And you should actually read it. It's not so difficult. I will just give the hint. So initially they just have some observation about S and T, and later they have, in the second part, they just use, say, the G is an element in SL to Z. Then you are asked to show that G is generated by some combination of S and T, and you just take two cases as G, if G is of this form, and when G is of this form, when C is not 0 and when C is 0. So so in either cases, for this case it's so easy, and for this case they just use the division algorithm over A and S, A and C, and they just reduce this case into this, and you are done. And that's how they are doing the proof. It's not so difficult that I need to tell you. But the major thing is that SL2Z is generated by two elements, one of whose order is finite order, which is 4, and another order is infinite. So that's the key observation. And the next, yeah, So the next, so we were saying that SL2Z is generated by two elements, one of whose order is finite and another order is infinite. The next thing, which is a surprise, is that the SL2Z is actually generated by finite order elements as well. Like both elements are finite order. So earlier it was one was finite, another was infinite. Yeah, I mean it is visible, right? Yeah. So the next exercise, that's how they are developing the theory in terms of problems. So they introduce this as a problem. So show that SL2Z, which actually I just showed on the screen as a screenshot, is generated by S and ST. We already calculated that S has order 4. Now we are saying that the order of ST element is 6. Yes. So SL2Z is generated by two elements whose order are finite. And isn't it surprising and interesting? Like initially it was generated by an infinite element, and then here it actually generated by finite elements as well. So it's so easy to do calculations, and there are many ways to think about this problem, and one can actually use what was done earlier, that we showed that SL2Z is generated by S and T. Here we have S. We just want to show that S and ST generate T, and that's how it's to be done. We know that S square is identity minus identity, and then we just do some calculation to just get T and S. With ST, we are taking these two elements. We get S square T, and S square is minus identity, and it will land with T. And then simple calculations again, you will conclude that S square T is T. And that's the proof is done. We are moving to the next section, which is subgroups of the full modular group. So in this section we are going to discuss subgroups of SL2Z, its subgroups. So as I said earlier, we are developing the theory to get the roots and later see the full picture of the tree. So I will state the definition of the principal congruence subgroup, which is denoted by gamma n, and we will see that later on that what is level and what is, you say, the congruence subgroup. And then so this section, the 2.2, is pretty long, so I will cover some part in this video, and we'll continue the further part on the next video. So here is a definition on the screen, that the principal congruence subgroup is defined to be, for each natural number n, the principal congruence subgroup of level n is denoted by and defined as follows. So they are just taking the matrices in SL2Z, satisfying the condition that for say that the matrix is A, B, C, D, it should be congruent to, this belongs to gamma n if it satisfies this congruence relation modulo n. And yeah, as you read over here, that in particular gamma 1 is taken to be the full modular group. Yes. And now we will see the example. Like, all this theory is so abstract for the first time if you just read it. And so yeah, so you should, I mean, I try to give an example. Say for we have n to be 2, then how the elements of the gamma 2 group looks like is a collection of these elements 1 0 0 1 and so on, and 3 4 2 3, I mean, like this and so on. So determinant should be 1, that you should always take care of, and they satisfy this congruence relation with mode 2. So mode 2 these are 0 and mode 2 these are 1, so satisfying the relation. And determinant is 9 minus 8 is 1, which is what we want it to be. And for this case, n is equal to 2, I just try to create an generating element formula. I will show up over here. And what I am doing is over here is that alpha is congruent to 1 mod 2, and CB as a combined element is congruent to 0 mod 2, with a relation that alpha plus 1 is CB. I somehow believe that I am exploiting the definition itself by generating this formula, but it works. It works right. So yeah. So I will just give the overview of the next question. And in the next question, so one should be careful while constructing this. I will show the question. So the question is, and the hints is also given over there. So we are constructing a surjective homomorphism from the full modular group SL to Z to SL to Z mod and Z. Yeah, and where how the elements as matrices, say A, B, C, D, are mapping as A, B, C, D mod N. That's how the map is defined over here. And I won't provide the solution, but you should be very careful that it's a group homomorphism. That's clear. You can work on it. But when it comes to the surjectivity of a group homomorphism, what we naturally seek is that we take an element from the codomain and we try to uplift it in the domain. And if we are able to generalize that step, that lifting any arbitrary element, we are getting a pre-image, then we say the map is surjective. The issue is that the natural map, you can imagine that, oh, we can take the natural maps and map it over here. That won't work, and that will create an issue. And I will just explain it with an example, and then we will finish this video, and maybe I will continue in the next one. I mean, we are going to continue in the next video. So for n is equal to 5, when we have this map SL to Z to SL to Z and Z. So when we are talking about the surjectivity, we are taking an element in SL to Z, Z mod and Z, say it to be G 4 0 3 4. So it's the element is over there, right? I mean, here n is 5, right? So here n is 5, we take that it's 5. And the element is over here. Why? Because if we see the determinant, it's 16, and 16 with mode 5, I mean, the matrix element is still same, but the determinant is going to be 16, which is 5, which is actually 1 mod 5, which is which is the condition of the SL to Z, I mean Z mod and Z. So what I'm trying to say is that the determinant is 16, which is equivalent to 1 mod 5. So the condition that is the special linear, the determinant should be 1, is clear. So this element actually belongs in this group only. But when you uplift this element naturally, you are saying that, oh, just take the elements and map reversely, and it will work. Then you will see that this won't belong in SL to Z. The determinant is 16, which is not 1 over here. So natural upliftment won't work over here. So for surjectivity, you should think with more. And I will suggest, if you want to be able to think much, then you should follow the solution section. The proof is a bit constructive, I think. Yeah, so that's how they are doing. And remember this map, this map, how they mapping between two groups and subjective homomorphism. Group homomorphism. It will be helpful in the next lectures and even in the next exercises. And it will give some nice results. While solving the exercises, you will be able to see some good results. And we will continue in the next video. Thank you for watching. That's it.